elc138 22, a little bit hoarse from mowing the yard. Quality factor. First question. Quality factor is the ratio of the inductive reactance to the resistance of the wire that makes an inductor at a certain frequency. You can Google that term, the quality factor of an inductor, and you can learn about it. So I'm giving you a problem that has an inductance of 2 henries and 60 hertz, quality factor of 95. So you can figure out the resistance because it's the only unknown, and then if you put an ohm meter across it, that's what you should read. So quality factor is pretty straightforward. It's not one of those things you use a lot, but it's one of those fun facts you should know. For the following circuit, now getting into AC a little bit, is you're familiar with voltage and an AC voltage instead of just the 24. If it's an AC source, it will have AC. You're familiar with resistance. You know what the 1, 0, 1, 2 mean. They're node numbers. That's not changed. With inductance, LT Spice uses an L to denote it as an inductor. And the unit that it uses is the Henry. It does the calculation for you, or is internally part of the program. So, what is the reactance of the circuit? What's the resistance of the circuit? What's the impedance of the circuit? I don't specifically list a frequency here, so you would assume my frequency is 60 hertz. So you come up with the reactance, I give you the resistance, and then you can come up with the impedance of the circuit, which is the vector sum of resistance and reactance. Number 5, if a 24 volt 60 hertz coil has a measured current of 10 milliamps, what is the inductance value? So when you energize a relay coil, you could measure the resistance it takes to energize it. So we did that. We measured 10 milliamps. And so what I'm asking for is what's the inductance of that coil? So the impedance is what's limiting the current when you start getting into inductive circuits, and that impedance can be found, if you will. We're assuming R is 0, so all you have to do is work back out using the 2 pi FL equation equals XL. Okay, number 6, how can you know that a source has internal resistance? So voltage sources always have some internal resistance. By design, manufacturers of voltage sources, whether they be batteries or something like that, try and keep the internal resistance to a minimum, but it's there. A lot of times in a class like we've got, we don't worry about the internal resistance. It's considered something called stiff, because the internal resistance is very small as compared to the load resistance. And if that's the case, we can ignore it, which makes the circuit analysis much easier. But in reality, it's there, and it's an important concept again to know. So what's the internal resistance of a battery that under no load reads a voltage of 12? And with a 2 amp load, the voltage, and this is the voltage at the terminals, reads 11.9. So this is really an Ohm's law problem. So with no load or no current, you read 12, and now when you're flowing 2 amps, you read 11.9 at your battery terminals. That means you've got internal resistance, and you're dropping 1/10 of a volt with 2 amps flowing, so you can figure out exactly what that internal resistance is. It's just an Ohm's law problem. 8 through 10, analyze a circuit. It's got 25 volt source. It's got a resistor coming out of the source of 3K, and then it goes to two parallel resistances, 2K and 5K, going back to the power supply. And I just want to know the current through each resistance and the voltage drop across each resistance. So when we get off in the weeds, sometimes we got to come back and just do a simple DC circuit, because that's what the class is about, right? 11, a resistor of 2K ohms passing 3 milliamps would have what voltage drop across it? Ohm's law problem. A resistor of 2K ohms passing 3 microamps would have to dissipate how many watts? That's actually a power problem, but I do give you enough information to solve it. So we do a little basics, and then we go back into some new terminology. There is a part of a DC motor that spins, and what is it called? Now, over the course of your career and your life, you will probably hear it called many different things. There is what I consider the one proper thing to call it, and the rotating part is called the armature. So you may hear it called a rotor, but a rotor is an AC designation. So on a DC motor, the rotating part is your armature. The stationary part of a DC motor is your field. Okay? Now I'm saying all that. Well, it's okay. The stationary part is called your field of a DC motor. Most DC motors. Okay? An AC term for the stationary part would be the stator. But I try and teach students that when you're talking about an AC motor, you're talking about rotor and stator. When you're talking about a DC motor, you're talking about armature and field. So I'm just trying to introduce those concepts to you. You may see books where it's called rotor and stator in a DC motor. You will hear that term, I almost guarantee it, but you need to flip the switch in your brain when somebody says it's a DC rotor, that they really mean field. And if they say it's a DC, if they say a DC stator, they really mean field. And if they say a DC rotor, they really mean armature. I'm just trying to get y'all in the proper terminology. Number 15, what's the time constant of a circuit with a 3,000 microfarad capacitor and a 1K resistor? Capacitor is charged through a resistor, and I think you may have looked up the time constant already on a different worksheet, so I'm just coming back to try and reinforce that, if you will. You can look up time constants if you'd like on Google and get there. 16 to 20. Complete the table based on a simple circuit of fixed internal resistance of 10 ohms. So I've got a 10 ohm internal resistance, which is pretty high. I've got a load resistance that varies, and I've got 12 volts feeding the load. Okay, so what I've done is I've gone and created me a spreadsheet that is the same. So 12 volts applied, it's a series circuit. My source resistance is within my battery, or within my power supply, and then my load resistance is the load resistance that I am putting from positive terminal to the negative terminal of my power source. So these are definitely a series circuit. So my total resistance would be 11. My volts applied would be 12, so my current would be equals the 12, if you will, divided by the series resistance, which would be 10 plus 1. And you can use the cells in Excel if you want to and come up with the formulas and it makes it easier to fill out the table. If you want to be an engineer, that's where you want to head, to where you can use this and use these tools to make math easier, because you're going to do some calculations as a one-off, but a lot of times you want to study stuff. You're going to do a lot of calculations in a hurry. Okay? So if I wanted to use cells and I wanted to find the current, I'm going to back up. He says, I'm going to reference the cell that my volts applied in is 12. So what I'm going to say is equals $. And when you use a $sign in Excel, you are giving it a specific reference to a cell. That cell, I don't have my window big enough, is actually B8. So it's $ B, column, $8. Now, if you put your 12 somewhere other than B8, then that's different. So Ohm's law tells me current is voltage divided by resistance. So I'm going to divide by. And my resistors are in series, so all I do is sum them up. So I'm going to say A2 plus B2. A2 references the 10 ohm resistor. B2 references the 1 ohm resistor. And then I'm going to close that and I'm going to hit enter. And so now I have my current. So 12 divided by 11 is that. The nice thing about it is, if I got my formula right, I can copy that cell and paste this cell down, and now I have all my currents for all 5 problems. The source power is the power dropped across the source resistor. So from a power formula, I'm going to take this current, square it, multiply it times this resistance, and that's going to give me my source power. So this is C2. So this is going to be equals C2. I need it squared, so I can multiply it by itself, or I can do the up caret squared times my source resistor, which is A2. And that gives me the power dropped at my source resistor. Okay, I've got that worked out. I can Control C, copy, and Control V. Boom. Load power will be my current squared times my load resistance. So I can say equals my current squared, which is still C2, quantity squared times B2. And so there's my source power, there's my load power, and Control C, Control V. That's pretty quick, right? That's a lot better than doing all these calculations. And then my load voltage is my current times my load resistance. So here I'm having you do the power, but I just want to know the load voltage. We're putting 12 in. How much voltage are we actually getting across the load? So we're going to calculate that now. Load, my current is C2, my load resistance is B2, so my load voltage based on Ohm's law is C2 times B2. B2. And you see that I'm putting 12 volts in, I'm not getting very much out across my load resistance. I'm not getting a lot of power. I've got a lot of internal power, so my power supply is actually getting warm. And the reason this is done, I'm going to copy these down so you can see. is boy, this mouse is having fun today. Power is doing work, and so a lot of times we want to transfer power. Duke Power bills your house for the amount of power you use, so they want an efficient way to send power. We know that everything has internal resistance. Duke Power has some resistance. Your house is the load, and so what they're trying to do is they're trying to give you power. The utilities isn't the best example, because what you see here is that my best power transfer happens when my source resistance is equal to my load resistance. So what you see here is my load power is the highest when my load resistance is equal to my source resistance. Different way to say the same thing. On the other side, excuse me, on the other side of that, you see that it goes down. And so if you're trying to get the most power to your load, you want to make your load resistance equal to your source resistance. Now, your utility companies don't do that, because look what happens to your load voltage. It's only 6, which is half of what we applied. So to get the perfect power transfer for our house and utility, or the most efficient, then they would make it the same, but all our voltages would be half. And so things that are designed to work at 120 volts won't do very well at 60. It'll cause all sorts of problems. Where this comes into play, however, is the radio in your car. You want the biggest sound in your speakers, or if you have any kind of system where you are trying to get volume out, what you have to do is you have to match your speaker impedance with your source impedance. And so there's something out there called an impedance matching transformer. You don't care about the voltage, you're trying to get the maximum power out. So if you've got a stereo in your car and you're trying to get maximum power out, you've got to do something called impedance matching. And this is what this is showing you. And that's why I do it as an exercise. Alrighty. Boy, I'm hoarse. And let's see. I think that is the last problem. Yeah, it was 16 to 20. So you can calculate every one of these blocks by hand. You can go through and do it as a spreadsheet. I really don't care. I'm looking for the right answers. Anyway, I think that will get you through worksheet 22, and I thank you for watching.